Good morning, mathematicians. How's it going? I always ask that as if you can answer immediately. I always ask that before I've opened up chat. Good morning, math. So what's up with me doing that? Yeah, I don't know what's happening. What's happening in the world today? Let's go to ArXiv. We haven't looked at ArXiv for a while. Let's go see what's happening on ArXiv. That's a place to start. What should we browse? All fields. Yeah. Let's see, math. Math new. Just math new. Can you click on that? Unsteady Navier-Stokes equations. Interesting. P-potent and nilpotent matrices. Loop percolation in 5 and higher dimensions. Interesting stuff. Oh, I did have something I thought maybe I could work on. Computation I could do on stream. But I don't remember. Wow, it's crazy. This is just this is just what's new today. That's insane. So this is happening daily. 260 articles are happening daily. Mind you, there's probably a lot more happening right now because people are applying for jobs and postdocs and things like that. So yeah. Probably it's not like 260 papers on Christmas Day or something. But this is still wild. There's so much mathematics. 260 papers a day. How many mathematicians are there even? Wild. Fireworks. Newton polytopes of fireworks Grothendieck polynomials. What the hell? Free Tambara functors. Level-wise finite. We prove free polynomial G Tambara functors. Interesting. It's going pretty well. How are you doing? Nisha? Interesting. You see Grothendieck, you must click, yeah. Well, I'm not, I decided not to click on it, actually, but at least read the abstract. Hello, Daysen. Remarks on the Brouwer conjecture. I did see something about wavefront sets I was kind of interested in, because that is something to do with things I think about. Do I understand everything on my screen? Absolutely not. Probably I don't understand most of what's on my screen. Look at this, Combinatorists always coming in with like the 10 author papers. It's nice though. I mean, it's very collaborative. On the perversity of Chern classes for compactified Jacobians. Okay, that's definitely we're right clicking that. We're taking a look at this one. But I wanna go through more things here. Learning about blowups. Crazy. Yeah. I don't think I've actually learned it properly, to be honest. You know, I use algebraic geometry. I'm like aware of the concept of blow-ups, and more or less I do use that in some places in my work, essentially. You know, taking some like resolutions of singularities and stuff. But I've never really formally studied it, so I should probably do that. That's probably a blind spot in my abilities. Non-commutative marked surfaces. Wow, there's just so much stuff. I guess this is why I should search things based on fields. But then, you know, sometimes I worry about that. I'm like, well, if I just search like a certain tag, then what if someone decided to put something under a slightly different tag and I miss something interesting? Finishing your undergrad in math ed this semester before jumping into pure math in your grad. Nice. Well, good luck. Good luck. Congratulations. That's coming up. You find them elegant, the blow-ups? Yeah. I mean, it is I would say that it's more Tambara functors? Okay, whatever these things are, they're really things are popping off in Tambara functor world. S2ifications? What the hell? What the hell is going on? What are the kids studying these days? Finally started reading schemes on Hartshorne, and so far is not so bad as 3 years ago. Yeah. Yeah, that makes a whole lot of sense. Got bored and went to Vakio. Yeah. Yeah, Hartshorne's definitely a better book when you have already a little more experience under your belt with some of the things. I mean, I read some of Hartshorne, you know, like actually the first couple sections of chapter 2 are definitely readable introduction, but then I felt like, yeah, the rest was density of wavefront sets. Maybe this is the one that I scrolled past before. Well, we've only gone through like 100 papers so far. Imagine if I tried doing this every day. We could go there. Probably this isn't the most entertaining though. Algebraic proof of modular form inequalities for optimal sphere packings. Oh, interesting. That's very interesting. Okay, maybe I'll click on it. Hello, Seek. How's it going? I'm probably just going to keep, right-click new tabbing all of these papers, and then I'll get to the very end of this page at the end of stream, and then I'll be like, well, that's it. That's the end of stream. That's all our time for today. Simultaneous supersingular reductions of Hecke orbits. Eisenbud and Harris wrote a nice book on schemes. Yeah. Geometry of schemes. And I think they take the functor of points perspective in that one, right? If I recall correctly, they start off with that near the beginning. Okay, this is probably This is probably too boring. Let me click on some of the papers we got here. Let's take a look at what's going on here. Perversity of Chern classes. We prove some perversity bounds for the Chern class of a compactified Jacobian vibration, namely the kth Chern class of the compactified Jacobian has perversity at most k. Our results are motivic in nature. We also prove a filtration version of the conjecture, of some conjecture. Crazy stuff. You took a grad course on point set topology with some basic algebra. Nice. And instantly fell in love. Nice. Nice. Nice, yeah. That's a good pair of books to learn from, I would say. Is that what you're planning on doing in grad school? Some algebraic topology stuff? Or is that just you happen to enjoy that as well? Let's do this every day, but our goal is to understand only 2 words in the abstract. We prove. Done. I mean, I don't know. This vaguely makes sense to me, although the perversity bound is a little weird because I thought that had something to do with some sort of like, okay, there's I know in the theory of intersection cohomology complexes you also have this like some sort of bound called perversity, and then the thing that I normally think of is like perverse sheaves, the intersection cohomology complexes, those correspond to the middle perversity. And yeah, so actually I don't know what that bound is supposed to be. But it seems weird to me to say that a Chern class would have a perversity bound. That seems weird. Ideally, yes, your professor has some open problems on his blog, and you might try and tackle those when you have more background. Oh, that's cool. That's very cool. I feel like I would, I don't know, open problems are, I mean, in some fields I feel like they're maybe more bound, more abound, more, good, my brain's not working today. My roommate woke me up in the middle of the night, but I'm moving soon, so it won't be a problem for much longer. Yeah, I mean, for some fields, I feel like it's a lot easier to come across interesting open problems, and so therefore you don't have to like guard them as closely, because someone will. There's just so many that if someone you find out someone's working on that one, well, I mean, you could publish at the same time or just pick a different problem. But I feel like. Certainly there's some fields where it's like, oh yeah, for an early grad student, like the tractable problems to attack are maybe fewer and far between. So a problem you face is when you construct a toe table of 2 groups that you don't know how to check that they are similar, and sometimes they are not. I see. So I'm not entirely sure what you mean, but I'm going to try and take a guess here of what you're talking about. And maybe, do you mean when you write the multiplication table for 2 groups? Like for Z mod 3? 0, 1, 2, 0, 1, 2. You mean something like this? Is that what you mean, Seek? You shared your passion with someone on Discord, and he is luring you into studying motives. Oh, cool. Seems a mathematician got stuck with the Grothendieck's plan and went on studying analogies. Yeah, yeah. Well, I don't know. I think, I think I don't know much about the category of motives, but there's, well, we talked about it on stream the other day, but obviously there's reasons why people want to study it. Right. Got to be, fruitful idea. And there's already partial results and stuff, right? So clearly it's working. At least try to find weaker versions of some of the statements to chip away at. Yeah, as is the usual process, yeah. Any operation, you mean how to know for big inputs that the two tables are similar? Yeah, sorry, I'm still not understanding what you're saying. And what do you mean by similar? Like the two tables are permutations of each other? So like for the dihedral group, what if we called it, is this the center or not the center, but the rotations of the triangle that we have, R0, R, what's the 180 divided by 3, R60, R120. You mean like comparing two tables like this and seeing if they're similar? Right. Okay. Yes. So that is what you mean. Yeah. Well, the thing is, for these tables, I mean, this is not a good way to check if two groups are isomorphic. Yeah, it's just simply not a good way. Especially like once you get beyond groups with 4 elements, which, by the way, there's only 2 groups with 4 elements, so it doesn't take very long to check. Then just this just simply is not. This is not a fruitful approach to check to see if two groups are similar or not. Unless you're a computer, I don't know. There's I don't know how computer algorithms work that try and determine whether two groups are isomorphic or not. Maybe they do some crazy stuff with tables or something. But if you're not a computer, this is just not a good way to do this. You'll be taking group theory, advanced linear algebra, and intro analysis this semester. Any advice? Any advice? No, not really. I mean, no advice specific to those things other than other math courses. But I recommend making use of flashcards. And the hierarchy is basically definitions is number 1. You better have all of your definitions memorized precisely, like symbol for symbol in the exact order, right? So like the definition of the limit, you'll have like for all epsilon greater than 0, there exists a delta greater than 0, such that x minus a less than delta implies f of x minus L less than epsilon, right? So that's the definition, say, for the limit, right? So this exact sequence of symbols in this exact order, you better have it committed to memorized and be able to pull it out. or I mean, you don't need to have this memorized on day one, but I'm saying every single time you come across a definition, you should put it in a flashcard and you should commit it to memory. The next thing then, of course, are theorems, especially like big theorems and key theorems in the course, especially ones that you find yourself using. You find yourself using certain theorems again and again, right? So the first thing to have memorized is the statements of those theorems, and again, much like the statements of the definition, the exact, precise wording as in the textbook, and make sure that you can use it correctly. And then you'll also want to have on hand proofs. I think it's also worth memorizing. So I know the fun part of math is not memorization, and that's, I could have been a good biologist if I was more interested in memorizing things. Or maybe, I don't know. Maybe I couldn't have. Maybe I would have sucked at biology. But I was not in it, but nonetheless, it's important to, and so like, it's important to memorize a certain amount of proofs just to remember proof techniques, and in case you're asked on a test to prove a similar thing, then you can reach back in your memory bank and you go, well, the statement of this theorem reminds me of the statement of this theorem, so let me think about the tools that are in that proof. And so I would carry, like, in my jacket, flashcards with me, and then while I was waiting for the bus, I would try and look at the proof, and I'd see if I could, or I'd look at the theorem statement, and then I'd close my eyes and see if I could go through the proof in my head and see all the symbols and stuff. And then, of course, at the beginning, I could not. It was impossible. I'd barely get through a sentence. So that card goes to the back of the deck, and I try the next one, next one. But by the end of the semester, as I kept trying this every time, I was waiting in line for something or I had a minute, eventually I could start to go through some of these things in my head. So that was very useful. The other thing that you want, and actually I don't know where to put this in the hierarchy, so this is definitely the main hierarchy. You need to know your definitions. As long as you have that, if you forgot the theorems and the proofs, you can at least maybe survive the final. But there's another very important one, and I'm not saying that this goes beneath the others, but that's to have examples. So write down important examples with proof, right? So for example, have an example when you learn about continuous functions. So have an example of a continuous function, and then later you'll learn about absolutely continuous functions, or not absolute, but uniformly continuous functions. So make sure you have an example that you can prove of f that is continuous, but not uniformly continuous. But then also make sure you do have an example of an f which is uniformly continuous, right? Or in algebra, you learn about principal ideal domains, and you learn about unique factorization domains, and you learn about Euclidean domains, and some of these imply the other, and so make sure that you have examples, things that are one and not the other. So every time you come across a new concept, add that to your deck of flashcards. That would be my suggestion. Yeah. Good points from Jared. Boris used to memorize most of the point set topology counterexamples. Definitely a good idea if you're doing point set topologies. There's a lot of weirdness. There's a lot of counterexamples. That is definitely a course where I would actually say, if you're doing point set topology, then definitely the examples I would even put above the definitions, because it's so important to understanding what's possible and what's not. Then what's the better way of constructing a function? It's kind of hard for you, and then check whether the conditions are being fulfilled, like 1-to-1 onto. Yes, exactly. If you want to prove that two groups are isomorphic, well, the best way to do it is to write down a function show it's a homomorphism. And then I think it's better, if possible, to provide an explicit inverse, right? So if you have two groups G and H, I think it's preferable to, if you think it's an isomorphism, write down explicitly the inverse map and show that they both compose to the identity. Of course, life's sometimes hard, and the easier thing is to prove that, yeah, this is one-to-one and onto. Yeah, but that's a better way. I mean, it's kind of hard if you don't have an explicit example. So maybe you're asking me this question because you have an example in mind of two groups that you wanted to prove were isomorphic from some exercise from a book. If you can point me towards that, then it would be easier for me to talk about how you might go about doing that. I don't know if you've learned the first isomorphism theorem yet, but that is, generally one of the best tools to prove that two groups are isomorphic. Long line was your favorite because you can play with it and it gets weird spaces, long ray, closed ray, and long circle. Yeah, there's definitely weird stuff going on there. Absolutely. And Sorgenfrey plane? Really? I've not heard of the Sorgenfrey plane. What is that? Sorgenfrey plane. Oh, yes. This is ringing a bell. I mean, it's been like 8 years since I took a point set topology course, but this is coming back to me. Oh yeah, this is actually a really important, anti-diagonal, not the diagonal. Oh, this is interesting. But this is ringing bells. Yeah. Realign under the half-open interval topology. The Sorgenfrey line and plane. Therefore, rectangles that include the west edge, southwest corner, and omit right. I see. That is a product of Lindelof spaces, being every open cover has a countable subcover. Okay. That is not itself a Lindelof space. Interesting. That is freaky. An uncountable discrete subset of the space that is non-separable subset of a separable space. Wow. This is crazy. That is crazy. That's good stuff. Shade on bio. Not actually any shade on bio, to be clear. I mean, I'm very interested these days in like health and longevity. Here's what I would actually do if I was 20. Here's what my recommendation would be. Go be a quant. Go make $300K a year until you're like 30, and then retire, and then just become an anti-aging scientist. That would be my dream for myself now. If I could go back in a time machine, I would work on. That's what I would do. I would go be rich so that I would have like no pressure, and then I would just go hang out and become like a self-taught person, and hang out in the like anti-aging longevity space. I could do that too. Yeah, I may still, but the problem is in 10 years, if I manage to get a quant job tomorrow, like in 10 years, then I'd be in my 40s. Actually, maybe that's not so bad. Brian Johnson pipeline, maybe, but I'm True, but I'm more about the Aubrey de Grey pipeline. I've talked about him on the channel before. I don't know if you know about Aubrey de Grey. Like, I think stuff that Brian Johnson's doing is interesting, but Aubrey de Grey actually has a PhD in computer science and published a paper on a certain kind of generalization of the four-color problem, but which deals with like unit distances in the plane, and yeah, and then went on to go start some like longevity research company. So that's a little more that trajectory sounds a little more in line. You know, I mean, yeah. I don't think Brian Johnson's stuff is like totally 100% scammy, but it is a little, he's trying to like push some products and stuff, which is fine. I don't think it's necessarily that obnoxious, the extent to which he does such things, but yeah, I mean, I feel more drawn towards a computer science guy who published papers and then went off and did longevity research. Can I explain how derived functors work? Sort of. I can start. I mean, what's the best way to do this, actually? Actually, I might need to put a pin in it, and I might need to put a pin in that. And well, I guess the idea is well, okay. So there's like the fully general. There's like, the fully general, like if I have two derived categories. They could be of sheaves, or maybe X and Y stand for categories of R modules or something. I habitually write bounded derived categories. Doesn't even necessarily need to be that, right? I mean, so what do we want? We want to somehow find a way that maps complexes to complexes and chain maps to chain maps in the target category, right? And so we need to find some particular way of doing this, and so how do we possibly build these things? And presumably, like ideally, we might want to do this by computing things in terms of the functors of the underlying category, right? One might hope that there's some way to lift functors from the underlying category. So suppose I have functors from the category of R modules to S modules, and then somehow can I take functors between these two categories and lift them to a functor in the derived category? Well, of course, there are certain kinds of functors that we definitely can, right? So, for example, if f is exact, well, then we can simply take, like if I have a complex with differentials d, of course, this, I can simply apply f everywhere, and I will still have a complex. Right. This will if f is exact, it preserves the complex. So great. So definitely we can lift functors in this sense. Now, how might we lift functors? In another sense? Well, first off, we have okay. The ideal situation is if a functor is exact. Well, you might say, well, the next thing to do is just simply not an exact functor, but then we could also consider functors that are exact on one side, right? So for, classic example are like the Hom functors, right? These are just, left or right exact on the one side. And so the next step up would be, okay, how could we try and repair like these things, right? And so in order to talk about this, well, let's sort of think about the process of how we talk about the derived functors. So I guess this is what our Hom, because this one's left exact. I always get them confused. So let's think about how we build up our Hom. What's the normal process that we do? Well, if you wanted to compute, say, what our Hom is here, well, we oftentimes talk about just computing our Hom at a single object, right? So like this is exactly what this complex is exactly what the X complex is of two modules. But okay, so we actually want to somehow view this. We want to somehow view our Hom as actually being a functor between the derived categories of modules. So we want to take B and we want to realize it as an object of the derived category. Well, there's sort of two ways to do this, right? So one very natural way is to, and there's this whole fancy language of triangulated categories and T-structures, is we can look at, sorry, I know there's so many comments I haven't touched, way too many comments. Okay, maybe tomorrow we'll start by looking at these comments. Yeah. So I'm gonna finish this train of thought, maybe browse the comments, and we'll come back to all of this tomorrow. But so one thing you could do is you could just take a complex where all your maps are the zero maps, and you just put B in the middle, right? And now we've taken this object of our category, and we've essentially taken, an object of the derived category that represents it. That's perfectly reasonable, but something that's more akin to the way that we compute derived functors is we take a projective resolution of B, right? Do I want projective resolution in this case? I always get the sides mixed up. Yeah, I always get the sides mixed up slightly, but let's just say it's a projective resolution on this side, whatever. And then, okay, I'm wrong up to like a switching of arrows and changing projective to injective, right? So what is a projective resolution? Well, we take a bunch of projective objects, right? Oh no, I guess I want injective because I'm feeding it into this slot. Yeah, I think maybe I want an injective resolution. Okay, like I said, it doesn't. I mean, okay, yes, it matters to actually do the calculation, but the idea is the same. So, okay, say we have an injective resolution. And the thing is, this also represents the object, right? Because we have, remember our notion of isomorphism in the derived category is quasi-isomorphism, which says we have a map of complexes that induces isomorphism on cohomology. So we just take the inclusion maps everywhere, and we take the identity map here, and because an injective resolution is an exact sequence, we see that, yes, this actually, this map will induce isomorphisms on all the cohomology. And so therefore, this object is isomorphic to the one above. So this is another way to represent the object B in the derived category in terms of the sequence. And so this explains sort of the first step in the process of how we apply derived functors to sequences of this kind, right? Because this is exactly like the process that we do to come up with x is you now apply hom. What should I say? You now apply hom everywhere. Right, and the sequence that you get out, what should I say? So like the result of the complex x. What should I say? Oh, this is the object. A is just a singleton object, right? But so this functor applied to at least these simple objects here, is just the cohomology of the complex you get out here. Well, yeah, sorry, rather, this is defined to be the cohomology, but like the image of like the X functor itself is represented by this complex. Okay, so we'll have to come back to this tomorrow, because office hours are almost up. But that's good because it gives us a goal, something for us to aim for and start with tomorrow, talking about derived categories. So I don't remember what amenable even means, new wave infantry. But I do know some professors at my old university, one of my old universities, used to work on amenable groups. In some cases, you'd put examples above theorems. Well, yes, I agree in the case of point set topology. Not this time. Counterexamples. Muncre's using the name Sorgenfrey plane is enough for you to not liking Muncre's? Why don't you like that name being used? I am too old, yeah. Can I prove the long line is a smooth, connected, one-dimensional manifold, but not paracompact? Connected topological is fine. Don't know how to give it a smooth structure. Interesting. Zongshu. I wish I had seen that. I wish I had seen that comment before. Well, if you don't know what a derived category is, I mean, then we need to start there. Oh, you don't know what a projective object is either. Okay. Well, I see. I should have been reading the comments, because those are maybe things that you need to know before you learn derived functors. Yeah. So I would first. Okay. So you don't actually. We could just ask about ext and tor. Right. I see. Okay. You just want an explanation of ext and tor. I see. Yes. Okay. So we don't have to do full blown derived, functors between derived categories to talk about ext and tor. Yeah. Okay, we'll come back to that tomorrow. But in the meantime, I recommend look up what a projective module is, and an injective module. You'll probably want to know what those mean. And okay, maybe we'll come back to this tomorrow. Maybe we should make a Google form listing all of our BG. I don't know what that means, but yeah, maybe we should have some official list somewhere. I don't know. They define them as derived functors. I mean, that's true. They are derived functors. Um, uh, well, I don't think they're so bad. I mean, tomorrow, if I remember, we'll go and do some computations. We'll do some examples. They're not so bad. Well, depending on what you know. I don't know. Go look up projective and injective modules, and we'll all meet back here tomorrow